So thank you very much for joining us. And just as we wait for other participants to get to join us, yes, I can see you can be able to see me and you can hear us. Just as we wait for other participants, I'll do just a few things. The first one is I am going to share the meeting link in the chat box. I've already done that. So if you have a friend, a colleague, or someone that you think they would find this session worth their time, so please pick it up and share with them. Number two, we are also live on LinkedIn. So if you have your phone close by, please feel free to check it and see whether we can be able to hear us. I know Gatimu, Baron, they are members of my team. You're here. Please check and let us know that the audio and the video is proper. Then we get started. Baron, can you get to see that, please? Can you get to confirm that?
Okay, engineer, I'm on it.
Okay. Just check and then let us do that. So as we wait for other participants to join us, I will play one awesome video here that will be setting the context of our session today. And our session today, of course, is on storm water. So this video will be a little bit more of a broad perspective, and then our expert is going to narrow it down for us. So my work is just to do the broader work. All right. Fantastic. Thank you for confirming. So I'll just share the video to create for us to set the pace. And then after that, we will be able to give it away to our guests. So 1, 2, 3, let's have the video going. All right. So I'm sharing it. That one, share sound. Great. So please confirm if you can be able to see my screen. Again, you just drop a 1. Just drop a 1 and I will be able to know that you are able to see. Super. Great. So let's go.
Those dense congregations of people and buildings have made possible economies and lifestyles our early ancestors could never have imagined. Cities, those dense congregations of people and buildings, have made possible economies and lifestyles our early ancestors could never have imagined. Whether you thrive in or despise the concrete jungle, there's no denying its benefits. Putting all the people, houses, jobs, stores, offices, and diversions in one place gives us humans opportunities that wouldn't be possible if we all lived agrarian lifestyles spread out across the countryside. But there are some negative consequences that come from cramming so much into such a small area. At no time is this more clear than when it rains. Managing the flow of runoff through a city is an immensely complex challenge that affects us in so many ways, from public safety to property rights, from the environment to the health and welfare of citizens. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about urban stormwater management. This video is sponsored by CuriosityStream and Nebula. Get 26% off at the link in the description. More on that later. The water cycle is one of the most basic science lessons we learn. So basic, in fact, that it's easy to forget how relevant and important it is to our lives. Take a look out your window when it's raining, even when it's raining hard, and it doesn't seem that significant. Some of the rain soaks into the ground, some gets taken up by plants, some gets caught in puddles, and some runs off downhill, usually into the street. One of the biggest challenges in a city is the proportions of all these different paths that water can take. All those streets, sidewalks, buildings, and parking lots cover the ground with impervious surfaces, which means that instead of water infiltrating, it runs off toward creeks and rivers, swelling them faster and higher and filling them with more pollution. One of the biggest impacts on the environment of building anything is its effect on how water moves above and below the ground during storms. Multiply that to the scale of a city, and you can see how remarkably we modify our landscape. Instead of acting like a sponge to absorb rainwater as it falls, urban watersheds act like funnels, gathering and concentrating rainwater runoff. In this video, I want to walk you through some of the infrastructure cities use to manage this massive challenge and a few new ideas in stormwater management that are slowly taking hold in urban areas. Like most of the biggest challenges of building and maintaining a civilization, the negative impacts from adding impervious cover don't befall the property owner doing the adding, but rather the people downstream. Just like dumping pollution into the river carries it away to the next guy, it's easy to make bad drainage decisions into someone else's problem. That's why most large cities have rules about how to manage runoff and flooding when new buildings or neighborhoods get built. Drainage reviews are just a normal part of the process of obtaining a building permit these days. If you live in a major city, just do a search for your local drainage manual to see the kinds of things that are required. Increased runoff has been a problem since people started living in cities in the first place, and the first way we handled it was simply to get the water out and away as quickly as possible. That's because runoff creates flooding, and flooding causes billions of dollars of property damage and many lives each year. This solution is in the name we still use for how cities manage storms: drainage. When it rains or when it pours, we try to give that runoff somewhere to go. Most cities are organized so the streets serve as the first path of flow for rainfall. Individual lots are graded with a slope toward the street so that water flows away from buildings where it would otherwise cause problems. The standard city street has a crown in the center with gutters on either side for water to flow. This keeps the road mainly dry and safe for vehicle travel while providing a channel to convey runoff. But the streets aren't the end of the line. Eventually the road will reach a natural low point and start back uphill, or will have collected so much runoff that it can't hold it all in the gutter. At this point, the water needs a dedicated system to carry it away. In the past, it was common to simply put all the runoff from the streets directly into the sewage system. It's a well-developed network of pipes flowing by gravity out of the city. Why not use it for stormwater too? Well, there's actually a really good reason not to do that. At the end of each sanitary sewer system is a wastewater treatment plant that was almost certainly not designed to process a massive influx of combined sewage and stormwater runoff at the whims of Mother Nature. In the worst cases, these plants have to release untreated wastewater directly into waterways when it's too much to be stored or processed. That's why most cities now use municipal separate storm sewer systems, usually abbreviated as MS4s. These are networks of ditches, curbs, gutters, sewer pipes, and outfalls solely dedicated to moving runoff from everywhere in the city to the natural waterways that eventually carry it away. These inlets aren't just places for clowns to hang out. They usually represent a direct path between the street and the nearest creek or river. Just to be clear, there's not usually any type of treatment happening along the way. These sewers are not for waste. Whatever you put in the storm sewer system goes directly into a waterway, so please don't dump stuff in there. It's easy to see why cities try so hard to get stormwater out as fast as possible if you look at the floodplain. This is just the area most likely to be inundated during a major flood. Land is one of the most valuable things within a city, but its value goes way down if it's exposed to flood risk. No one wants to build something on land that could be flooded. That being said, humans are notoriously bad at assessing risk, and no matter where you look, you're likely to find development near creeks and rivers. Getting the water out quickly reduces the depth of flooding and thus shrinks the floodplain. That's a big reason why you see natural waterways in cities enlarged, straightened, and lined with concrete. You can see in my demo, for the same amount of flow, the channel with lots of vegetation moves water more slowly and thus at a higher depth. The channel with smooth sides gets the water moving faster and thus reduces the depth of flooding. But channelization isn't all it's cut out to be. It's ugly for one. No one wants a big dirty concrete channel as part of their surroundings. But channelization also worsens flooding downstream for the next guy and degrades the habitat of the original waterway. It didn't take long for cities to realize you can't just keep widening and lining channels to keep up with the increased runoff from more and more development. That's why most cities now require developers to take responsibility for their own increase in runoff. By and large, that means on-site storage for stormwater. Retention and detention ponds act like mini sponges, absorbing all the rain that rushes off buildings, streets, and parking lots, and releasing it slowly back into waterways. This shaves off the peak of the runoff with the goal of reducing it back down to or less than it was before all those buildings and parking lots got built. They also help reduce pollution by slowing down the water so suspended particles can settle out. On-site storage is a pretty effective solution and one you'll see everywhere if you're paying attention, but it still treats stormwater as a waste product, something to be gotten rid of. The reality is that rain is a resource, and natural watersheds do a lot more than just getting rid of it. They serve as habitat for wildlife, they naturally clean runoff with vegetation, they divert rain into the ground to recharge aquifers, and they reduce flooding by slowing down the water at the source rather than letting it quickly wash away and concentrate. That's why many cities are moving toward ways to replicate and recreate natural watershed functions within developed areas. In the US, this is called low-impact development, and it includes strategies like rain gardens, vegetated rooftops, rain barrels, and other ways to bring more harmony between the built environment and its original hydrologic and ecological functions. It can also include better management of the floodplain by using it for purposes less vulnerable to flooding, like parks and trails. One low-impact strategy is permeable pavement, and I have a video just on that topic if you want to check it out after this one. One thing I have to mention when talking about flooding is vehicle crossings. Any location where a waterway and a road cross paths, whether it's a bridge, a culvert, or a low water crossing, there's always a chance of flooding getting so bad that it overtops the road. If you ever see water over the top of a roadway, just turn around. Half of all flood-related deaths happen when someone tries to drive a car or a truck through water over a road. If you can't see the road, you have no idea how deep the water is. And even if you can, it only takes a small amount of swift water to push a vehicle down into a river or creek. Water is heavy. Even when it's flowing slowly, floodwaters can impart a massive force on a vehicle. Even if it didn't, most cars will float once the water reaches the floorboard anyway. Some cities have warning systems to help block roads when they're overtopped by floods, but it's not something you should count on. It just isn't worth the risk. Find another way. As they say, turn around, don't drown. Just like cities represent a colossal alteration of the landscape and thus the natural water cycle, we're also going through a colossal shift in how we think about rainfall and stormwater and how we value the processes of natural watersheds. Look carefully as you travel through your city and you'll notice all the different pieces and parts of infrastructure that help manage water during storm events. You'll see plenty of ways to get water out and away from buildings and streets, but you hopefully also notice elements of low-impact design, ways of harnessing and benefiting from stormwater on site, treating it like the resource that it truly is.
Thank you, thank you very much. That was a very informative video. And I will just be going straight to taking takeouts or what we've been able to learn. Just before this, when I was listening to this video, there was this story that came to my mind. It was around April or here in Kenya, where we experienced the highest rainfall that we've ever, like there has never been such intense rainfall before in our country. And what happened is there was a lot of property destruction. There was a loss of lives. There was a lot of, that's when people came to realize that we have been ignoring one of the most important aspects when it comes to safety of our infrastructure and, of course, the safety of our people and ultimately the public health of the people that we serve. I'm going to quote one of my gentlemen here. He's saying that engineers have saved, or they are at command to save more lives than even doctors. And this one, he was talking in the context of water engineers, stormwater management, and sewer management. If you have, for example, in the context of developing countries, we have combined sewer systems where we are combining stormwater and sewer. And what happens is during the rainy seasons, the sewers do not have the capacity to handle all the runoff. So the next thing you see is everywhere there is a lot of sewer streaming all over the streets. So I will just give this chance to our beautiful people who are joining us. If you can represent your country, drop a flag of your country, where you are. And then I would like you to take just a minute before we give it away to our guest. Just a minute. What is your takeout from that? And what is the actual context of stormwater management in your nearest urban area? For me, our urban area is something else. It's something else. I'm not going to talk about it. I'm going to talk about it as the last person. So please take it away. We can have a few people represent your country. I'm seeing South Africa, Uganda. So let's go. Who is there? Who is ready to say a word? Let me know. Who is ready? Yes,
Hello.
Baron.
Good day, everyone. I'm from South Africa. So yeah, I'm here also on behalf of WhatsApp. So I think for me the biggest takeaway was how stormwater, like integrating the existing structure in stormwater, and how it is important to convey stormwater safely to discharge it, because failure to do so, it will result in damages of structure. So my biggest takeaway was the importance of stormwater. And yeah, I think that's my biggest takeaway. Thank you.
Thank you, Baron. That's a fantastic one. We need to take stormwater management seriously. Let's get to hear one more person from another country, South Africa represented. Who else?
Yes. Hello.
Yes, Joseph.
Hi everyone.
Hello.
I'm Joseph. I'm from Zimbabwe. Yes. So my key takeaway was when there was the highlight of managing stormwater as a resource rather than viewing it as an enemy. You know, if it is managed well, it is actually a resource. So yes, that was my.
Super, brilliant. We need to recycle this water and reuse it. Thank you. One more person, Tanzania. I can see people from Tanzania. Kanza, come on. What do you do with stormwater in your country?
Good afternoon. Good day, everyone.
Yes.
Hans Kanzia from Tanzania. Well, in our country, stormwater has been a problem, especially in most urban areas. We fail to control it, and hence, anytime there is long-term rain, all roads are going to be flooded fully, and mobility around the city becomes extremely difficult. So it is important to control the stormwater so as to not affect the economical and social activities of our communities. Thank you.
Absolutely. Thank you. We have had people from the south, from the eastern. So I've seen someone from the west. That's Nigeria. Nigeria, what are you doing with your stormwater? Let me know. Abayomi and Prince, what do you do with your stormwater? What is the state of stormwater management in your urban areas? All right, great. So just for the intro,
from Nigeria.
yes, please.
Hello.
Yes,
Can you hear
please.
me?
Yes.
Mukhtar, I'm from Nigeria. So we also use our stormwater to do similar things. We channel the water away from the urban cities down to the natural water habitats. So basically, just to channel extra runoff to the natural water course. So that's what we use it for in Nigeria.
Okay. So do you consider stormwater as an enemy or as a resource?
It's actually both. It's actually a resource in the case that it's a resource that we use it for here in Nigeria also. Somebody's calling me.
Okay. Yes, Prince, you can speak.
Yeah, good morning.
Good morning.
Okay, so basically, in some water, in some state in Nigeria, it's as a resource. I know in Niger State, there is a treatment plant where the stormwater goes there, they treat it, then return it back to the community for usage.
Absolutely. Thank you, Prince. And thank you, everyone, for sharing your perspective on what you are using stormwater or how you manage stormwater in your different countries. And today, I have the honor to present to you Engineer Sean. He is from Queensland, Australia. He has sacrificed his time to be with us today. And just before I get to introduce him, I would like to just read his bio and how we got to meet with Sean. Number one is I tend to perceive myself as a person who is attracted to the top 1% of the world. I'm attracted to the top 1% of the world. And this is what was outstanding about Sean. I got to see that he was nominated as the engineer of the year in Queensland. And I was intrigued. I was like, oh my, what does this guy do? What is it that is so unique? And looking at Sean, I came to realize that Sean is a chartered civil engineer with an impressive 19 years of experience across diverse projects. He has been working in engineering, in construction. He has been working in building. He has been working in roads and currently working also at ADG. And one of the other thing that was the intersecting part between me and Sean and the community that we are building is his ability to foster technical excellence, leadership, and innovation. That is one thing that was like a match for us, because when I also got to see what Sean has been doing, he is supporting the young professionals to be what? To be proper leaders of the industry. And over and above that, to own their technical expertise. So that is why I'm presenting to you, Sean, today, so that he can take away this and he will be better placed to introduce himself. So Sean, please take it away and you're most welcome.
Thank you, James. Thank you to Rhodes Hub and James as well for having me tonight. Absolute privilege, an honor to be here, and quite excited to talk everything stormwater. A great introduction. I think that sums up it pretty well. I guess to give a little bit more background. Yes, I am a civil engineer here in Australia. I've got 19 years industry experience. And I've also been a lecturer, a teacher at for adult tertiary for the last 10 years as well. So anybody that knows me knows that I love everything about civil engineering. And I also like to teach as well. I get a bit of a kick out of it. I really enjoy that. One thing that I've found in Australia, and I'd love to hear stories across other countries as well. I'm sure it's the same. But there's always a struggle with with people that would study through university or other sort of tertiary, and they will learn all of this theory and they'll be so knowledgeable, or so they think, until they join the industry. And then that first day, it's like a hit in the face of just how much you don't actually know, and you don't really know how to apply the theory to the practice. And I saw that and experienced that through my career. And so I thought I wanted to try and change that a little bit and help the industry. So that's where I created Quilty Engineering Hub. And we basically, our mission is to help people bridge the gap between theory and practice. So we want that practical learning. And so we do that through short courses, webinars like tonight, and also workshops as well for private consultants, for councils, municipalities, and individual coaching as well. So that's probably enough of an intro, I think, to get started. I do have on the screen now, hopefully everyone can see that. It's a nice, simple, easy way to subscribe to Quilty Engineering Hub. And what this does is it's completely free. and you'll receive monthly newsletters where we have tips and tricks and just information about what's happening in the industry. And we also, every now and then, will drop free design spreadsheets, design tools to help us in our day-to-day tasks of civil engineering. And we also have technical articles or write-ups where we might just uncover some theory and explain how it comes together in practice as well. So if anyone's interested, it's 2 easy steps. Step 1, you just scan that QR code to head to our website, enter your email address and join, and then you're part of our community going forward. It's really exciting to see how many countries are joining. Obviously, within the African continent, within Australia, I saw someone from France even, which is pretty cool. I love that. But tonight we're going to talk about stormwater, in particular pit and pipe design, or inlets. In Australia, we tend to call them pits, but we just mean stormwater inlets. And so we're going to start with, we're going to have 3 quick presentations tonight. Now, the first one's going to focus on the rational method. So we're talking about when it rains, how do we quantify the amount of water that's coming down onto our catchment? The second course is going to be inlet design. So once we understand how much water is flowing through our urban areas, how do we design an inlet and force that water and capture that water into our inlets? So that's the inlet sizing, which is the second step. And then the last course is our pipe design. So once we're able to capture that surface runoff, how can we design the pipes to actually convey those flows appropriately? So it's a bit of an introductory type course tonight. We'll go into a little bit of the theory, but then base it around the practical real world examples. And we might have a few, not so much calculations, but sort of helping to get into that calculation space. So we'll get started. Please let me know if anything does go wrong or doesn't show like it should. You should see the PowerPoint presentation starting now. Okay, so first we're going to cover the rational method. Now, one of the best things about this webinar, we're going right around across the world, different countries all around the world, and yet that video spoke to it as well. We're all experiencing the same problems, the same issues, and we're all designing to the same environment, if you like. We all experience floods. We all have built up urban areas, and we all have issues where we're not sure how to control the stormwater runoff. And it is, in fact, a two-faced entity. It is our enemy sometimes, and it is also our friend and savior a lot of the time as well. So we've got to manage that as a civil engineer and a civil designer. So the rational method, it is a very robust formula, I suppose, or hydrological model, if you like. So it helps us to quantify how much water will fall from the sky and run down a catchment. So this allows us to calculate that stormwater runoff. Now, I do start by saying it is a simplified method. There's many more complex methods that we can use as well. But this is a great way to introduce you into stormwater runoff. The rational method is the easiest one to pick up and to understand. When it comes to pit and pipe design, within Australia, probably 90% of pit and pipe design is undertaken using the rational method as well, because we're always talking about very small subcatchments for each individual inlet. So essentially, the rational method will allow you to take a location of interest, and then you can analyze that site using contours, topographical information to find the catchment. And then the rational method will calculate just how much stormwater is going to run down to your point of interest. We can use it in rural areas, and we can also use it in built up urban areas as well. So in this case, we can have a point of interest at the end of the road, and then we can analyze that catchment and work out how much water will run through at that location. So the rational method is a very simple equation. There's only 3 variables. This is the metric formula here. So the 360 is just to convert our units into cubic meters per second. This formula is over 150 years old. So it's been used all over the world for a very long time. So it's very well known in the civil engineering industry. So the three variables that we look at are the rainfall intensity, the catchment area, and the catchment response to runoff, or the coefficient of runoff. And those three things are all we need to get an estimate of the worst or the highest peak discharge rate of any catchment. So the rational method relies on two assumptions, and we really need to understand these assumptions because we're trying to simplify something that is very complex. Rainfall and catchment response and stormwater flows, it is very complex. There's lots of variables and it becomes very complicated if we want to try to mimic exactly how it works. So we assume two things. We first assume that a storm burst of duration equal to the time of concentration will yield the maximum or peak discharge rate. So if we have a catchment and our time and concentration is 20 minutes, we assume that a 20-minute storm burst will give us the peak or the worst discharge rate. So that's one assumption that we make, and it's not always true, but that's what we use for the rational method. The second assumption is that we assume the watershed or the catchment receives uniform rainfall during this time of concentration. And that's also not true. I think people will appreciate that when you have a storm and you're looking at a burst, the intensity or how much water is falling from the sky, that will fluctuate over time. But the rational method assumes that it's uniform rainfall during that time of concentration. So with those two assumptions, we can then proceed using the rational method. So with the rational method, we start talking about time of concentration. And the time of concentration comes into this I, or rainfall intensity value, that we use in the formula. The rainfall intensity is based on the time of concentration equaling your storm burst. So if we have a time of concentration of 10 minutes, we need a storm burst of 10 minutes. And that's the assumption that we make. So we need to understand rainfall intensity, but first we need to understand time of concentration. So the time of concentration is the time that it takes for stormwater runoff to travel from the farthest point of our catchment to our outlet. And now I must stress the farthest point, we are referring to time and not length. So when you look at your time of concentration, you have to find the longest time to get from the upstream end of your catchment to the downstream or the outlet of your catchment. And usually when we do calculations, especially when you're just starting out in the rational method, you'll assume a flow path. And many times you'll have to do maybe 2 or 3 flow paths and calculate the time of concentration. And it might be 8 minutes, 12 minutes, and 15 minutes for 3 different flow paths. And then you would take the longest time of those flow paths. And that doesn't necessarily mean the longest length. So just keep that in mind when it does come into to calculating the time of concentration. So with the time of concentration, there are various components relating to the catchment conditions. Essentially what we're looking at with the time of concentration is flow paths. How is that stormwater runoff running through your catchment? And that will depend on the type of surface we have, the grade, the treatment or the surface finish. Is it grass? Is it concrete? Is it a forested area? All of these things will change how the water flows through your catchment. And so we look at the overall total flow path from the top of your catchment to the bottom, and we can break it up into different flow components. And then if we add up those components, we get our total flow path, which allows us to calculate our total time of concentration. So these are probably the most common flow path components or time of concentration components, if you like. Certainly the most common that we use here in Australia in urban areas, and I'm sure probably the rest of the world as well. We won't have time to go through those in detail, but just to give you a bit of an idea, we look at roof to main system connection. So that just means how long does it take the rainfall to hit our roof and then to start spilling out onto the road, perhaps through a curb adapter or an opening where our downpipes will then discharge onto the roadway. So that will be one component of a flow path, and that would have a certain time. We can have curb flow. This is when the stormwater will be running down our road along our curbs, and depending on how long and at what grade that curb is, that time will obviously differ. We have pipe flow as well. This becomes important when we have quite large stormwater systems. So with lots of interconnected pipework, those times will add up for our time of concentration. We have channel flow as well. So these might be man-made channels that we're talking about. So maybe table drains or perhaps a large diversion type drain that we might have. We also have overland sheet flow. Now, this is usually at the, or typically at the top of your catchment and where you have a uniform surface type. So it might be a great big sports oval, for example, is a good way of thinking about it. So when the rain falls on that, it's going to slowly build up and then it will almost act like a thin sheet of water that's just flowing down that particular surface or the oval. So that's overland sheet flow. And then one popular one that we use here is concentrated overland flow. And this is typically where you have overland flow and it will run as a sheet flow for a certain period, but then it will build enough momentum and it will start to form its own rills or almost like a small gully that it would start to form. And when that water flows as a concentrated flow, it's much faster and it changes the way that that water behaves as it's running off. And so that's where we talk about concentrated overland flow. And in this case, it might be a natural channel that we look at. So they're just some. There's certainly more types of flow that we might encounter. But in an urban area, that will cover probably 90% of the catchments that we look at. So we'll look at our formula. Q equals CIA on 360. And now we're just going to break down each of those variables. So first we look at the coefficient of runoff. So the coefficient of runoff is the ratio of total runoff to total rainfall. So if your coefficient of runoff was 1, it means that all of the rain that falls from the sky and hits your catchment will end up at the bottom of your catchment. So this accounts for catchment infiltration and other runoff losses. We know in reality, when the water does hit our catchment, water will be trapped or stored in small depressions, perhaps. It might infiltrate into our ground in pervious areas, and it could be lost in trees, in transevaporation and a few other ways. And so this coefficient of runoff will help us quantify that, that phenomenon where the water doesn't actually make its way to the bottom of the catchment. So if we have a low C value, that tends to reflect pervious areas. As an example, if we had a C value of 0.5, we're basically simplistically saying that 50% of our rainfall will result in runoff, and the other 50% will be lost in the catchment. And that's why when we have pervious areas, we tend to have more water that is stored or trapped in the catchment. It filters into the ground, into the soil, the grass, the trees, and so our C value is less, and there's less runoff at the bottom of our catchment. When we look at impervious areas, so concrete, roads, roofs, we tend to have very high C values. Now, as an example, if your C value was 1, you're saying that 100% of that rainfall will result in runoff. Now, even in urban areas where it's predominantly impervious, sometimes always, like the whole catchment might be completely impervious, your C value may not be exactly 1. There will still be some losses that you might find, whether it's in small depressions and that sort of thing. So now we get to rainfall intensity, our second variable of the rational method. So when we talk about rainfall intensity, This is when we look at the rain or the rate of precipitation that's falling over a certain period of time. It's expressed as millimeters per hour for the rational method. But here in Australia, we have a resource where we can obtain IFD data or rainfall intensity data for anywhere in Australia. And we can also choose to obtain the rainfall intensity as a depth over whatever that storm duration is. And I point that out because when we start looking at rational method calculations, you want to make sure you're using millimeters per hour in your equations. And sometimes I've seen when checking people's work that they might use the millimeters and not the millimeters per hour, and you get drastically different results. So just keep an eye on that. Now, if we want to obtain our rainfall intensity, we need our time of concentration, and that's for the catchment specific. And then we need a storm frequency. How frequent are these storms likely to occur? And from that, we can then obtain an IFD table and then read some values from that. Now, I will point out, if you go to Quilty Engineering Hub's website, in our online courses, we have a free online course for rainfall in particular, and it talks about this in a lot more detail. So if you are interested, jump onto our site and enroll for free, and you can start looking at that online course. It will help explain the IFD tables, rainfall terminology. So when we start talking about storm frequencies and storm durations, and even how we start to look at hydrographs and how we analyze certain parts of the storm, all of that's in that free online course. So feel free to jump in, enroll, and hopefully learn a little bit more about rainfall. So once we have that information, the storm frequency and the time of concentration, we can then jump into an intensity frequency duration table. Now, we call them IFD tables in Australia. I know in a lot of parts around the world, they call them IDF tables. Exact same thing. We just like to do things a little bit different in Australia. So we've swapped those frequency duration names around, but it's the same table. So this is typically what an IFD table will look like. And so you'll have your storm frequency. So how likely are you to experience your storm in any given year? That's the percentages or the probability at the top there. And then you have your duration, your storm burst duration on the left column there. So with that information, we can then look up on our table and find our rainfall intensity for any storm frequency and for any duration. Anyone interested in Australia, you can jump onto the website. Again, all completely free, and you can just enter in any location and you will get your IFD data there ready to go. So that's our rainfall intensity values that you can see there. So there's some trends that you will see in the IFD tables, and I think it's really important to point out and for people to appreciate it, because when you're doing calculations, because you know these trends or what's likely to happen, if you get a different answer, you can usually spot your mistake because it doesn't make sense. Okay, so what I mean is, as an example, when you're looking at your rainfall intensity, the rainfall intensity will increase as the storm frequency decreases. So the storm frequency, if we start on the left, we have a 63% chance of that storm occurring any year. So it's a frequent storm. That's going to happen very often. And that rainfall intensity is relatively low. If we then look at our rainfall intensity over to the right and we look at a 1% storm, which is a very major and a rare storm, you can see the intensity will increase significantly. So the rainfall intensity will increase as the storm frequency decreases, as the storm becomes more rare. When we look at the storm duration, the rainfall intensity will decrease as the storm duration increases. So if you have a very short storm, it's usually a very intense, very severe storm, and so you have a very high rainfall intensity. So the 1, 2, 5 minute storms, you can see the intensity is very high. As that storm duration gets longer, So it's a 1 hour storm, a 1 day storm, a 1 week storm where it just sort of drizzles for a week. You can see the intensity will decrease as your duration increases. So knowing those trends, you should be able to spot any mistakes you might find, and you should be able to preempt or proactively estimate what might happen in a certain storm duration. So again, just a summary, the intensity, we have our millimeters per hour. That's what we want for our rational method. And we need the frequency and the duration of the storm that we're trying to analyze. So now we look at the catchment area. So our catchment area, it can be determined by a series of different ways of finding this information. And I always encourage people to get as much information as possible and not just rely on one source. And what I mean by that is your catchment could be determined using contours. It could be using council records. Aerial imagery can also help sometimes too. And I think one of the most important are site inspections. So even though you might have a contour map, it's always good to go out on site and actually walk the site and see what that catchment might do. You never know what might have happened since the original contours were picked up or surveyed and what's actually happening the day you start designing. So with all this sort of information, we can bring that together and then we can start to understand our catchment. So to identify a catchment, we need a point of interest. So this can be any point, but you've got to remember when we do the rational method, whenever you calculate a peak discharge rate or a Q value, it's always specific to a certain location, and that will have a specific catchment. So this point of interest, it might be a gully pit. If we're looking at inlet design, you might be analyzing how much stormwater runoff will be at the bottom of a hill, along a property boundary. If you're proposing to develop a block of land, you would want to know how much is flowing off of the whole site. So that will be along the boundary. Or it might be at the end of a drainage channel. You might be assessing existing channels to see what sort of flood conveyance it can withstand. So each of those points of interest will change the catchment area that we're looking at. Oops. All right, go back to that one. So then we come to the peak discharge. We have our C, I, and A variables. So now we can calculate our peak discharge, which is our Q value that we look at. So the peak discharge is the maximum rate of stormwater runoff at a specific location during a rainfall event. When we know the maximum flow rate expected, we can calculate our runoff for our catchments, but we can do so much more than that. We can look at inlets and pipe systems and start designing them. We can calculate drainage channel capacities. We can look at road capacity and see what type of a storm would actually cause flooding, whether it's safe controlled flooding or something that might be more hazardous. We can look at flooded widths and flooded depths and understand how that flood is going to impact our community and our area. And we can also understand freeboard and calculate freeboard to buildings as well. So this is all done by calculating this peak discharge using the rational method. So this is a rational method equation. And so you can see here, when you calculate the Q value, it's for a particular AEP or ARI. It's for a particular storm frequency. The C value that we use will be specific to that frequency as well, and so will the rainfall intensity. And the rainfall intensity will also be specific to our time of concentration for that catchment. So As I said before, we do have online courses as well. So anyone that is interested in learning a bit more about the rational method, feel free to check out our online courses. And what you do get with the online courses, we have hours of instructor-led video. We also have these design spreadsheets as well. So these are design tools that, that we hope the industry uses, and I know a lot of people do use them in the workplace for their day-to-day tasks. As an example, this one is built for Australian conditions, where we can look at a dynamic spreadsheet that will actually calculate our time of concentration and our rational method peak discharge rates based on our IFD data. The spreadsheet can also be used for looking at our rational method calculations and summarizes all of the storm frequencies at the end as well. So feel free to check that out if anyone is interested. All right, so that was the rational method, and it's, I'm sure, a bit of a information overload for some, maybe for others that have been using this in the industry for a while, not so much. But what we'll do is I'll just have a quick 1 or 2 minute break. James, if anyone has any questions, I'm happy for them to put it in the chat as well. We'll see how we go with time, but it will be interesting to see if anyone has any sort of thoughts or experiences or even issues that they find in their home country as well with regards to the rational method or any of the content that we cover here tonight. All right, so I'll just give it a 1 or 2 minute break and feel free to put in your thoughts and comments, and then we're going to jump into inlet design next.
All right. Thank you. Thank you very much, Sean. So to the dear participants, if you have a specific question that you would like for Sean to clarify, please feel free to send it in the chat box. We are taking a 2-minute break and then we'll be back. You can also be checking out, I've already sent the link to to the website, so you can be able to check it out and also subscribe and get the resources. I've actually even done mine right away. I'm doing it. I don't know, you guys can be able to see my screen. You guys are seeing my screen, right?
I might be sharing mine. I'll
Okay,
stop
no
sharing mine,
worries.
James, if you like. Are you sure? Yeah.
Yeah. No worries. Just proceed. So you can just go to, let me just go back. We have it here. You can check the home. You can go to, you click here.
Yeah, try sharing again, James.
Okay, let me share.
Yeah, try one more time. That should work now.
Okay. So this is the screen. Oh, okay. I don't know. You guys can see my screen. Sean, can you see my screen?
Yes. Yep.
Okay,
Yep.
Great. So you just go to home, to the Kilty Engineering Hub. You see, Engineers Australia 2024 Professional Engineer of the Year nominee. Yeah, big deal. Yeah. So once you do that, we talked about the free monthly. So you just click on the free monthly, and then you can just input your email. So for example, mine is mjamesmuridi at ronsab .org. Yeah, that's right. And you just, that's it, you get it. So you'll be getting all of this information, knowledge, you also get, look here, you have resume and interview tips, you have career networking tips, effective communication in the workplace, time management. Like, these are a whole resource that you can be able to benefit a few things here and there. So you see, like, for example, I wanted to know about resume, all of this information I'm able to access for free. Then once you do that, you can be able to access the free courses as well. And I think this is where we've said that you will be able to get the courses on Rainfall. So let me just click it right.
Yes.
So you go to
Online
online
courses.
courses, and then you go to Stormwater, Rainfall, and then you just click on enroll for the free course, and then that's it. You just enroll again, click on enroll. Let me just do let me get mine here now, because now
Yeah.
I don't want to miss it out. So I just use
So
that.
if you haven't yes, if you haven't signed up before, this is exactly what you do, correct? And then when you do sign up, you would just log in every time using your login details.
Okay, great. These guys are telling me I'm a robot. Okay. Do I look like a robot? Okay, let me see. Oh, great. Okay, fantastic. So I'm already in, guys. I'm already in. I hope you guys can be able to see that. So I just go to about the course, what is included, hours of instructor-led videos, several lessons organized to ensure effective learning and retention, detailed workable examples and calculations. There is guidance through the process of design, tailored specifically to Australian standards, but this one you can be able to adjust to your standards. Then exclusive design spreadsheet. So someone was asking about the spreadsheets.
Yes.
You can be able
So
to get
they're
them
with
here.
our, yes, the Rainfall one is just the free sort of introductory. So there's no design spreadsheet for that, but other courses will come with design spreadsheets. And when you subscribe, every now and then we'll give away a certain number of design spreadsheets as well, as a bit of a lucky draw for all of our subscribers as well. And that's it. And yes, you just go through the steps, and it's just a self-paced video. A lot of people that have these courses, they'll have this while they're working in the office. And when they forget something, or they're asked to do a rational method calculation and they haven't done one in so long, they'll actually open our videos and then sort of watch it and yeah, go through our calculations, and then they'll be able to sort of mimic the same process. So it's helped a lot of people out in the industry, which is always great to see. But
Thank you.
We'll keep going. I'm conscious of time, so I do want to hurry along a little bit. But thanks, James. Thank you for giving that demonstration. It was it's almost like you practiced that. All right, we're going to get into inlet design now. So when we look at inlet design, we're first going to look at the inlet terminology. Now, this is the Australian-based terminology. I'm assuming we'll have slightly different terms or names for certain things, but I've tried to include as many as we sort of have here in Australia. So hopefully if you at the end of this, you'll be able to speak like an Aussie when it comes to stormwater. We look at flow limits, and we also look at the flow terminology. So when we look at these catchments that we spoke about earlier with the rational method, we can then start to understand that it's not just a catchment when it comes to the flow. We have different types of flow, and we're going to get into that. But as an example, we'll have catchment flow, approach flow, inflow, and bypass flow. And then right at the end, we'll look at inlet capture charts as well. So as the video showed us right at the start of this presentation, we know that when we live in these urban areas, it's densely populated, and spatially we're very constrained. There's not a lot of space once we start building up these urban environments. We know that there's a lot of vehicle movement and a lot of pedestrian activities. So all of these things in mind, we know that we need to control our flooding events. So we need to look at all types of events, whether they are frequent, infrequent, or rare events. And when we do this, we look at three different aspects, and that is the convenience, safety, and also protecting our property. So it's not always about the biggest flood that we might see, where safety is definitely an issue. It's also for the very frequent storms where it's convenient. We don't want to walk down a footpath and always be walking through water, even in a small rainfall event. So they're the things that we manage as civil engineers and civil designers. So when we look at trying to manage the stormwater in an urban area, this is where we use longitudinal drainage. Or another more common term that we use is pit and pipe drainage. So this is a combination of stormwater inlets and interconnected pipes. So we use this as a gravity system to free drain all of our stormwater runoff. So we make sure that when the water enters our system, it is freely draining through gravity to discharge. Now, the majority of Australian systems discharge into creeks, rivers, or the ocean. There are some inland lakes, but the majority of our population lives on the coastal fringes of Australia. So almost every drop of water that drops in our cities will eventually make its way to the ocean. So when we look at longitudinal drainage, we use it to reduce flooding, but we also transfer this overland flow into our underground piped network. And we do this by strategically placing this infrastructure. So we position these inlets based on our own calculations and estimating what these floods are going to do. By doing this, we can be strategic and we can provide convenience, safety, we can reduce the risk to our community, and we can also capture our water for reuse. And that's an important one. That's where we start to turn stormwater as an enemy, and we can actually turn it into our friend and reuse this really valuable resource. And just a note here as well, and I'm sure the Roads Hub community will appreciate this. When we look at road design is stormwater design and vice versa. Stormwater design is road design. And I say that because in Australia, there are parts of the industry you might go through your career and become very good at road design. And sometimes some people won't be exposed to stormwater and they'll have a separate team to do their stormwater design. And so you have two different teams doing road only and stormwater only. And that can be, in my opinion, that's detrimental to the industry, because to understand road design, you need to understand stormwater as well, because the roads in urban areas in particular, the roads act as great big stormwater channels. So just a point that I like to make there. And in my opinion, I think you can't call yourself a great road designer without understanding stormwater. When we look at stormwater inlets, there are two broad classifications that we look at. Your stormwater inlet might be a sag inlet or an on-grade inlet. They're the two classifications. A sag inlet is when the inlet is positioned in the sag, so it's in the lowest point of the road. And so you get stormwater runoff entering from both sides of that inlet. An on-grade inlet is when the water approaches from only one side, being the upstream end of the inlet. And that stormwater inlet is on a grade, it's on a fall itself. And so the water will run towards the inlet. So there's many different names for these inlets. We call them inlets, we call them pits, we also call them gully pits. We have other types of inlets where we call them field inlets, which can also be named drop inlets. And then we have curb openings or side entry pits. So all these names mean pretty much the same thing. We have a structure that is trying to capture and convey stormwater runoff from the surface and push it into our underground pipe system. So when we look at inlet design, we need to understand the storm frequency. Now, tomorrow you'll be able to ask James all about this because he would have finished his rainfall course. And in there, we talk about storm frequency. Now, we will, when we look at storm frequency, frequency, we typically break it up into a minor storm event or a major storm event. And when it comes to inlet design, the inlet design typically is all about controlling our minor storm event. Now, there are exceptions to the case, but generally that's what our pit and pipe design is doing. It's controlling our minor event, and we shouldn't rely on our pit and pipes to convey our major event if we can avoid it. These are some examples of typical storm frequencies that we would use for different types of development here in Australia. So feel free, obviously, to watch this later on and maybe compare with your own country to see what the AEP or ARI storm frequencies are, depending on your development category. So when we look at curb inlets, in Australia, we have different inlets depending on what part of Australia we're looking at. Now, the environmental conditions and the rainfall, just the way it rains, is very different in a large continent like Australia, and obviously a continent like Africa. A lot of the audience would appreciate this too. At the north end of Australia, we have very high rainfall intensity, very severe storms that drop a lot of rain very quickly. When we get to the bottom of Australia, it's the exact opposite. The storm events are very long durations, but the rainfall intensity is very light, very long days, weeks of rain at a light intensity. So our stormwater inlets need to be designed differently depending on what the stormwater rainfall patterns and how it's going to be conveyed through our catchments. So these are three inlets, if you like, road inlets or gully pits, but they're very different. The top one is a side entry pit. And so this is typically what we'd see up north in the tropical areas, in the tropics. And that just has basically channels and just curb openings and no grates. The middle one is just a grated inlet. So it does not have a curb opening. These are susceptible to blockage and they're not very effective. And the bottom one is a combination inlet where we have the grate, but we also have the curb opening. So to look a little bit deeper into the terminology and the elements that we have the curb opening itself, a lintel, which is a prefabricated, basically a structure that supports that curb opening itself. Now that curb opening drops, so behind that concrete that you can't see, hidden behind that is a trough that actually grades. It's like a channel that grades towards the chamber. We have the the grate itself that then drops into our chamber and then connects into our piped system. We also have curb transitions. So typically we would construct the curb leading up to our gully pits once the gully pit was already installed. And then we have these little breaks between the curbs, and that's where we would hand form that concrete to have a nice smooth transition from our curb to our inlet. We have field inlets. So the previous one were what we call gully pits. These are field inlets. As the name suggests, they're usually placed in open fields. So parks, sports fields, grass sort of areas. Now we have three different types of grates. We have the flush mounted grate. So the grate sits flush with the surface. We have elevated grates, which is the top right corner there. And then we have dome screens as well. And they all serve different purposes. But one thing I like to point out when we're looking at any of these inlets is that we do need to maintain them. So that top right picture there, that was after a storm that I went. I'm a bit weird like this. When it rains, I like to jump outside and look at all the rainfall and see how these pits work. A lot of people like to stay inside, but I do the opposite. Anyway, it was a reasonably frequent storm. I would say it's probably a 63% type storm, a storm you would typically see once a year. So it wasn't that bad. But then after a couple of days, I went back there, and you could see all this leaf litter was just resting on top of the pit, on top of the grate. And so the problem is, if we don't maintain these and we leave all of that debris there, the next storm that comes through, that inlet will be not working to its full capacity because we're already leaving it blocked full of leaves and debris. And you can imagine if that happens after a few storms, that the inlet becomes almost useless, and that could cause all sorts of issues regarding flooding. So with our field inlets, they're a little bit simpler. We basically have our grate. We can have an optional concrete apron. So it's just a concrete surround. And typically that's used to control scour, so the water doesn't scour and erode all the soil around the inlet. It also helps for maintenance as well, because there's less chance that the grass and the vegetation will grow over and start blocking that grate. And then that drops into our chamber. So that's the main terminology, and hopefully you can find some similarities there with the systems that you use. Now we're going to look at flow limits. So before we calculate how much runoff our inlet will capture, we must assess the approaching flow heading towards our inlet. And the reason why we do this is we ensure that there is a safe flow width, the flow isn't too wide, and we ensure there's a safe flow depth. And what we use to assess how hazardous an approach flow might be, we use the product of the depth multiplied by the velocity. And when we multiply the depth and velocity, we get a good understanding of how much momentum is actually pushing through in that approach flow. And then if we keep that depth velocity product below a certain threshold, we tend to warrant that as safe flooding or safe approach flow. Anything beyond that threshold becomes unsafe, and then we adjust our road design or our stormwater inlet location to bring that level down. So we can see here, that's our flooded width, and you can imagine that depth will increase as the more water builds up and accumulates running down to that inlet. Now, it's not just vehicles that we are concerned about, but also pedestrians as well. So here we have a bus stop, and we have our approach flow running down our curb, and we can see that that flow width there is something we need to manage, because when buses will stop and allow pedestrians on and off, we don't want a flood to be running through, potentially causing people to slip, and even from a convenience perspective, where it starts getting a bit too wet too often. So when we're looking at road design, we are always assessing how much capacity a road does have, and it's something that's very important. And so what we've done in one of our courses, we've got a design spreadsheet that allows you to enter in your road geometry, the crossfall, the width, the curb type, and it will give you a table of the capacity of that road for any given grade. And so that allows you to pick any particular road you might have. It might be an existing road or a road that you're designing. And then you can see, depending on the grade of the road, you can read across and work out where your safe flows are and where they're not. And so all the red cells that we see there, that's a dynamic, it automatically updates. So when you read across, and if your value is in the red, it's showing that it's an unsafe flow, and then you've got to redesign it. So something that's really useful, and a lot of people like to use that in their workplace as well. So that looks at the capacity a road has, or how much stormwater runoff a road can convey before it becomes unsafe. And again, all the values that we enter in there, you can change those. So these can be for any country all around the world. You just tweak those values. So I won't go through these in detail. We're conscious of time, but you will be able to go through. These are typical examples of the the flood limits or the flow limits that we use. So as an example, I might just pull out one or two here. If we're looking at a minor road, that flooded width that's running through our road, if it comes to an intersection, we want to make sure that the flow running around an intersection is less than 1 meter or 1 meter maximum flow width. If that flow width is wider, then we need to put in additional stormwater inlets to capture and push that water underground. Oops, sorry. Now, I talked about the depth velocity product. So that's a value or a threshold that we use. So as an example, a DV or a depth velocity product, if you had water that's running across a road, so say it was a floodway, and then you had to have vehicles allowed to sort of drive through there safely, we have a depth velocity product less than or equal to 0.3, and that's our threshold. If we take our flooded depth multiplied by a velocity and it's more than that 0.3, we know that's becoming hazardous and we deem that to be unacceptable. So it's a great way to check for those design requirements. Again, I won't run through all of these, but they do have some different DV, depth velocity products there as well. And this time it's not water that's running across the road, but it's water that is running parallel to your road through your curbs. And you can have a DV product of 0.6 or 0.4, depending on certain requirements. All right, so we understand the terminology. We know what we're the types of pits that we might have. We also looked at the flooded widths, so what's deemed to be appropriate or not appropriate. So that's how we find those values. So now we can understand the flow terminology. So when we're looking at the catchment, what do we call these different flows? So this is where we have catchment flow, or I call it QC, lowercase c, approach flow, QA, inflow, QI, and bypass flow, QB. So before we jump into exactly what those values are, first thing that we need to do is we need to understand our catchments. So we mentioned this in the rational method course just previously. So we can obtain contours, site visits, survey information to really understand what's happening in the catchment. Once we do that and we understand how the land is graded, the topography, we can then understand how our roads are going to behave as well when it comes to stormwater. So we can understand our road falls, and where we have a road that is on grade, we know straight away that we need on grade pits. If we have our road and we find that there's sag locations, we know that we need to have an on grade, a sag inlet at those sag locations. So as an example, we might have analyzed our catchment and we found that this road had a crest, say at this location. So we understand where we need to start positioning these inlet pits. Because it's on grade, we would need on grade pits along these sections of road. We can understand how the flow behaves at the intersections as well. And then we can start looking at flow limits or the flow width, the maximum widths allowed. We can also understand how our lots are grading as well. So this is a residential development, but it could be an inner city area. It could be a rural residential area. But when we have the topography, we can then understand how those lots will be grading. In a similar manner, if this was a proposed development, this is how you could also start designing your development, designing your road geometry, and also designing your lot grading as well. Where would you like these lots to fall? And that's where we start getting into earthworks modeling, designing, retaining wall placement, and all sorts of fun stuff as well. So we know that when we have our road crest, it's going to push water in opposite directions. So it makes it very easy to understand how this water will behave. We also need to understand how our road geometry or our cross-sectional profile looks as well. This might be existing roads that we might be assessing, or it might be proposed roads that we're going to design as well. As an example, if we have a crowned road with a two-way crossfall, we can start to understand where these flows are going and how they're going to behave. In a similar way, we can look at our curb returns. So at intersections, if we understand where our roads are grading, we can then start to understand how that intersection flow or that stormwater flow will behave at the intersections. So now we come to the flow terminology. So the first thing that we look at is catchment flow. So the catchment flow is the flow that's approaching our inlet. And when we talk about catchment flow, it's only the catchment for that particular inlet pit. And then we use the rational method to calculate what this flow is, what this peak discharge rate is. So as an example, if we had some stormwater inlets in our pipe system, let's look at this individual stormwater inlet. Now remember, when we spoke about the rational method, when we're calculating a peak discharge rate or a Q value, it's always to do with a specific location first. So this inlet is going to be our specific location or our point of interest. So knowing that point of interest and understanding how our catchment behaves, we can work out what that catchment is. So that is what we would call the catchment flow. The flow rate that's coming off of that is our catchment flow. We do the same thing for the inlet on the other side of the road, assuming this is a two-way crossfall road. We can then calculate what that catchment is, work out the area and also the rational method, peak discharge rate. Now that we know our catchment flow running towards our inlet, we can then start to understand inflow. So this is the total flow that the inlet will capture and convey underground into our pipe network. Now, when we look at inflow, we need inlet capture charts to calculate these. So this will be your flooded width heading from upstream of the road, heading down towards your inlet. This is what we call approach flow. So we looked at catchment flow, and next we're going to talk about approach flow. Now that approach flow will drop into the inlet, but that inlet will have inflow, and that will be limited. It won't capture everything that approaches. There will be a threshold. Now, once it captures as much as it can in the inlet, sometimes there is excess flow that is not captured, and that actually heads down as bypass flow. So a small amount of flow might actually head downstream. So this is what we call bypass flow. So this is the remaining flow that is not captured by our inlet. And we can calculate the bypass flow by taking our approach flow minus our inflow. So the remaining is our bypass flow. Now, that bypass flow causes an issue because the inlet downstream, we would have done our catchment. So we'd have a catchment flow, but then all of a sudden we're adding this bypass flow as well. So this is where we look at approach flow. So if our inlet is at the top of the catchment and there's no inlet further upstream, we're right at the top of the catchment. Our first inlet, we would look at the catchment, and that would be our catchment flow. Now, because it's at the top of the catchment, there is no bypass that's coming into this catchment. So our approach flow heading towards the inlet is equal to our catchment flow. So what happens is that approach flow heads towards the inlet. We have inflow that is captured by the inlet. And then in this case, we've got bypass flow. So when it comes to the next inlet downstream, we do the same thing. We work out our catchment. We would work out a catchment flow, but then we have to add that extra bypass flow to work out our approach flow for that downstream inlet. So what you end up having is this cascading effect where you need to account for this bypass heading down to each of these inlets. Now, I won't go into too much detail now. I know time's running out now, but there are times that I've seen when checking people's works or designs where they will assume that the inlet just captures everything. And whether it's manual calculations or whether they've used computer software and they haven't set it up correctly, and so the inlet just takes 100% of that approach flow. And that is a very dangerous, very risky move, because that's not in reality what's actually going to happen. We need to make sure we assess and account for these bypass flows, because that is usually what happens or what causes major flooding issues. Okay, so when we look at the inlets, we need to understand how much flow any of these inlets are actually going to capture. So this is done in a couple ways. We can use mathematical equations that can estimate how much stormwater an inlet can capture, or we can use laboratory testing, which will then have proven results based on a real life-size scale model of what's happening. This is an example that was done in South Australia, where they constructed a life-size road pavement, essentially on hydraulics and an inlet, and they would have a flume to run the water down, and they would adjust the crossfall and the longitudinal grade of this road and change the inlet configuration. And they would then record what's actually happening with these inlets. Then they record and put that onto a chart. So it's available for us engineers and designers to actually look up and understand what's happening there. Another point I like to make is you need to have an inlet chart for every different type of inlet. You cannot use the same chart if the inlet configuration is going to change. So if your curb opening is deeper or wider, you can't use that same chart. If anyone is interested, obviously reach out to me, but I can help people design and help them with the theory in creating these inlet charts if you do need. And that goes across the world as well, not just Australia. So when we look at the inlets, we need to understand the hydraulic performance of these inlets. So how are they actually going to work? When we have inlets in a sag condition, the hydraulic performance is based on, or it's influenced by, the ponding depth above the inlet opening. So the water's coming from both sides into this sag, this low depression area. And that means that this inlet is really in a pond. The water doesn't go anywhere else. It just sits at this inlet and tries to force its way in. So that's where the ponding depth, or how deep that flooded water is going to sit above that inlet, that's what really drives the performance. And then obviously the physical dimensions of the inlet, the curb opening and the grate opening as well. So as the water approaches from either side, the more water that approaches, it will start to fill up. So you'll get deeper water, if you like, sitting over that inlet. So the performance will change as that water depth increases. The deeper the water, the more water that inlet will capture. And then it's very different when we look at on-grade pits as opposed to sag pits. So for on-grade pits, the performance is based on, again, the physical dimensions of our inlet. So whether it has a grate, the size of the grate, the type of grate, and also the curb opening. But then the other thing that comes into is the road longitudinal grade and the road crossfall. So the steeper the crossfall, the deeper the channel becomes between your curb and the road. So the steeper the crossfall, the more water it will capture. And then the flatter the road longitudinal grade, the water is going to be approaching at a slower velocity. So it has more time to force its way into the inlet. So the flatter the road, the more water it will capture. A very steep road, and you'll start to get more bypass flow and less inflow. So looking at our chamber here, this is where it gets a little bit more tricky with on-grade inlets. So we have our grate that's going to capture and then discharge water out into our pipe there. And then anything that isn't captured will obviously end up as bypass flow in that case. All right, I think we're going all right for time. We're doing pretty well here. So again, we'll have maybe 1 or 2 minute break. I'm going to grab a quick drink of water as well. And then we're going to get into pipe design. So we looked at rational method, we looked at what happens when it rains and how we can quantify how much water will hit our catchment and run off of our catchment. And now we've just looked at inlet design. So what do we do with that surface runoff? How do we capture that and then push that underground? So next, we're going to look at, once we've captured that water and now they're entering into our pipe system, what happens with that? All right, I'll give you guys a couple minutes. Again, any questions, throw them on the chat. And if we don't have time tonight, I'm sure we'll have probably a few maybe LinkedIn stories and comments to sort of go back to the audience as well with some answers. All right, so a couple minutes and we'll get back into pipe design.
So as we wait for Ignatian to take a break, if you have a question, please feel free to drop it in the chat box. Or also, if you have feedback or something, you can take this minute to air it. So take it away. Okay, and I'm back. So we're going to jump into pipe design now. So hopefully we've still got everyone online and we're keeping you entertained. And this is where we kind of pull it all together. So we have our rational method to work out when the rain falls from the sky, how do we quantify how much water is coming onto our catchment? We looked at inlet design. So now we understand how we can capture that stormwater
and push it into our underground systems. And so now we look into pipe design. So what happens once it's underground? So when we look at pipe design, first we'll look at the network elements. So the actual objects that we're actually looking at. So we have drainage inlets, which we looked at in the previous course. We have access chambers, and then we have our underground pipes, obviously, and we also have outlets. So these are all gravity-based systems. So it needs to be able to free drain naturally. So all of them will have some sort of an outlet where the stormwater can finally discharge somewhere. So our drainage inlets, I think we're all pretty comfortable with that now. So we know that these will capture our surface runoff. This controls our flooded limits. So that's our flooded width, our flooded depth, and our depth velocity product. And this redirects our flows underground into our pipe network. We also have access chambers. So as the name suggests, it provides access. And this is important for maintenance. So when we have blockages or sediment buildup is another big problem with pipe systems, we can actually physically get in there and wash and clean out those blockages. Typically, we have an access chamber at any change of direction. So as your pipes change direction or angle, as they change grade or level, we would have one of these access chambers here in Australia. Also at pipe junctions, we would create these access chambers so that water can enter into the chamber and then flow on the outlet. Of course, we have pipes. So this is what we use to convey our captured runoff from our inlets. Obviously, multiple pipes interconnected within a system, and that forms our longitudinal drainage. They can be single reaches too. So you could look at a pipe system where it might just be a simple culvert that's just going across the road from an upstream to a downstream location. So again, gravity systems, but this means that these pipes need to discharge somewhere. That might be into a detention basin, into a bioretention system where we have a specific soil media that filters and cleans that water to allow that water to actually discharge as cleaner, semi-treated water. We can discharge them into rainwater harvesting tanks. If we're doing a new development, we might have our stormwater pit and pipe system discharge into an existing pit. And of course, we have our head wall outlets as well. So the reason why we use these head wall outlets is once that water does discharge at a certain point, the head wall, which is a structure you see here, it provides a stable and controlled point of discharge. And then on top of that, we need to have some sort of scour protection. So once that water jets out of that outlet, that will very easily erode bare soil, but also even if it was a grass-lined swale or drain, depending on the velocity, it will start to scour and erode that grass as well. So that's where we have, like this example, we have dumped rock, where we can control and slow that discharge velocity down until it's acceptable at a low enough rate where it won't cause any sort of ongoing damage and scour. So looking at the terminology now, when we're looking at pipe design, these are a few things that we need to look at. So first we understand that the pit that we call it, it could be called a chamber or it could be called a structure, but they all mean the same thing. It's a physical chamber that's in our pipe network. Obviously our pipes. We have our pipe length. Now from a design perspective, here in Australia anyway, we measure our pipe lengths for design based on the center of the chamber from center to center. So it's not the physical pipe length for our design, it's actually a theoretical length that we use for design purposes. We have our pipe cover, which is really important in our pipe design. So that's the physical soil, earth, road pavement that you have above our pipes, and that protects and allows any loads from the surface to distribute evenly enough so the loads aren't too excessive, causing damage to our pipes. We have our pipe slope. Now, pipe slope is, I've got here as the letter here, SO, and I just want to point out that you shouldn't confuse the pipe slope with friction slope. Now, we don't have enough time, obviously, to get into a heap of calculations in this case, but when we look at the actual calculations of flow and hydraulic grade line, we start talking about friction slope, and that's very different, or can be very different, to your pipe slope. Just don't get those two confused. Looking closer to our chamber, we have our invert, which is the lowest point of the inside of our pipe, our obvert being the highest point of the inside of our pipe, and our crown. That's the highest point, but it's on the outside of the pipe. When we look at cover requirements, it should be to the crown of the pipe. I have reviewed a lot of designs in the past, and some people will just use the obvert of the pipe for their cover requirements. But sometimes, depending on the pipe that you use, you might have a very thick wall that will actually reduce the actual cover that you would have in reality, and it could become a non-compliant design. Typically, we would have a drop through our pit as well, from the upstream incoming invert level to the downstream invert level. So when we get into pipe design, the pressure head becomes very important. This philosophy needs to be really understood and appreciated. So essentially, within our pit and pipe system, the force that we're looking at is our pressure head. It's the force that the water exerts due to the weight of the water above it. Now, the more or less the pressure head that you have, as this pressure head changes, it will affect your flow rate, or how quickly that water is going to be passing through your pipes. As an example, if we have a small amount of pressure or pressure head in our system, we'll have a relatively low velocity. That column of water that's in your chamber is trying to force its way through because it's a free draining system. But if we increase our pressure head, we'll find that if our pipe is the same diameter and the same slope and nothing changes, if our pressure increases or our pressure head increases, our velocity is going to increase as well. And again, if our pressure head or that column of water was to increase again, just the sheer weight of that water and gravity doing its thing, it will actually force that water out at a much higher velocity. So that's important to understand, because when we start getting into pipe design, that pressure head is going to fluctuate through your system. And then you can use that knowledge to create more efficient designs, or to understand where designs might fail or might succeed. So this is where we look at hydraulic grade line, or HGL. So the hydraulic grade line represents a pressure head in our pipeline. So we looked at the pressure head just at the chamber, but that pressure will change and fluctuate throughout your whole system. So a hydraulic grade line basically shows a theoretical line where that pressure is actually building up to. So the flow velocity is a function of our hydraulic grade line and not the pipe grade itself. And this is where it comes into play, where we look at the pipe slope versus the friction slope. It's the friction slope that you'll see on your hydraulic grade line, and the friction slope is what will force that water through your system. So you might actually, in some cases, you might change your pipe design slope and nothing changes in your hydraulic grade line. And that's because the friction slope is what governs how that pipe works. So here in Australia, there's 3 different ways that we can model pipes, or we can design for pipes. These are 3 standard approaches, or 3 hydraulic design philosophies that we use. And this is all over Australia. In every state and territory, we have the same approach. So we have a simple, steady flow open channel model, which is what the top image shows. We can analyze it slightly differently and look at steady flow, but using a pressured grade line model. So that's a typical HGL, hydraulic grade line analysis. Or we can look at complex, unsteady flow in our systems. And basically the top one, the first one, is the easiest, the quickest, and more suited for concept preliminary design. The middle one is what we would use for detailed design. And then sometimes, in some cases, we might have to get into the complex model, looking at how it fluctuates over time, and then how storage comes into it and detention and that sort of thing. So the first two are all about steady flow, which means our discharge remains constant through each link, whereas the bottom one is unsteady flow. For your discharge rate will actually change throughout the pipe as it goes through. So obviously that's much more complex to actually design for and analyze. So this is a great way to first get into pipe design. And in particular, if you just want to undertake pipe design without any computer software, it's very easy to just have pen, paper, calculator, and you can run and design your pipe system for a concept or for a preliminary design. Now, once you've done this model, you would then have to get into detailed design and run a proper hydraulic grade line analysis using a pressured system. But just to get started, this is a great way to start off your design. So using the open channel method, essentially what it does is it assumes your flow running through your system is filling up your pipe until it's just shy of the obvert of the pipe. So essentially your pipes are really just acting as great big open channels, and the water doesn't build up beyond the obvert level. So it simplifies it, and it does become a bit conservative. Your pipe sizes will be slightly larger than probably what they need to be, but it's a very fast, effective way to get that first initial design to get an idea of what those pipe sizes might be. When you get into detailed design in Australia, you must get into the hydraulic grade line analysis. The open channel method is not sufficient for a detailed design. So this is where we look at the true interaction of what the flows will be doing through your pipes. So this becomes more efficient. Your pipe sizes will reduce slightly because you allow for that water to build up pressure, to have that pressure head to force more water through than you did with the open channel model. And then in some cases, you might need to look at unsteady flow models. Now this one will be dependent on time. So unlike the steady flow models, where you're looking at a peak discharge rate at a split point in time, this will actually analyze what happens at, say, 2 minutes, 3 minutes, 5 minutes, 8 minutes, and so on. So as the time progresses, your flows are going to fluctuate quite dramatically. A much more complex model, and definitely you will need computer software to run that, and it's only rarely needed in special circumstances. So there are 3 models. The open channel model is used for concepts and quick calculations. The pressurized grade line model is used for detailed design. And then sometimes we'll use the unsteady flow model. And this is typically when we need to look at real storms or a range of different storms, not just a peak discharge rate, or when volume needs to be considered as well. So the next couple items that I'm going to cover off that will come close to finishing for tonight is just a couple things that I've seen over my career that can really influence a design, and a couple things that are sometimes overlooked, and sometimes it's overlooked right up until the end of the design. And then when you actually take in these considerations, your design just simply doesn't work. And that's an awful spot to be in, and not always a good conversation that I've had to have with people to basically say, your stormwater design doesn't work because you didn't check these certain things. So this is where we get into tailwater conditions. Essentially, this is starting our hydraulic grade line at the downstream or the outlet level. So we need to understand, where does that hydraulic grade line start from? So this is essential for any hydraulic grade line analysis, and this can really influence your design. So we've tried to simplify, as we do as engineers and designers. We try to get something very complex and we try to simplify it or put them in compartments, in tables and forms. And so we've got 3 different cases that we're going to look at. So imagine your pipe is discharging at an outlet. This is going to look at how we start the hydraulic grade line, which is what we call the tailwater level. So this is one scenario that would happen. You might be discharging into a lake where you have a standing water level, or it might be a detention basin where that water will be at a certain level for a certain storm. And so in this case, we need to know, where do we start our hydraulic grade line for this event, for this pipe network. So in this case, if the tailwater, so the downstream standing water level, if that tailwater is above our pipe obvert level, then our starting hydraulic grade line is set to the tailwater level. So that's where your HGL will start. And I have seen cases over my career where some people have started at the obvert level and they just pick that as an arbitrary location. But in fact, if you're discharging into a standing lake or a detention basin, that might be starting a lot higher than your obvert level, which could actually ruin your design. We then have this case where our tailwater level is below our pipe obvert level, but our tailwater level is above our critical depth at the outlet. So if that happens, we set our hydraulic grade line to be at the obvert level. So we just simplify it and then just take the obvert level in this case. And then we have the third scenario where our tailwater level is below our invert level. So if this happens, the water is essentially escaping, or what we call freely discharging. The tailwater level is not impacting how our water is exiting from our outlet. So when the tailwater level is below our invert level, or it's below our critical depth, when this happens, we start our hydraulic grade line level at the normal depth of our pipe outlet. What that normal depth is, our hydraulic grade line can be at that level. So you can see it becomes a bit lower, so you can get a bit more of an optimized, efficient design. That's something to consider when looking at any design. You must first assess your tailwater conditions, and that's for any stormwater pit and pipe design, whether it's discharging off the side of a hill, discharging into a drain, into a detention basin, and if it's discharging into an existing pipe network. And that's what we're going to cover up next. So this is when we're connecting into an existing pipe network. In urban areas, we know that we are constantly developing and generally we're increasing our population. So we're always looking for new locations for new developments to discharge to. And a lot of the time we have to rely on existing stormwater pit and pipe systems where we connect into. So when we look at this, we essentially have an existing system on the right-hand side, and in the red, we see a proposed system that we're proposing to build or design for. But then we've got to ask ourselves, where do we start our hydraulic grade line for our pipe design? So before we start our tailwater condition, or where that water level is going to start for our pipe design, we first must understand how the existing system is performing. Once we understand how that water is performing or what's happening within that stormwater pit and pipe design, then we can adopt a tailwater level because we understand where those water levels would be in the existing scenario. So this pit may have a minor event, keeping in mind stormwater pit and pipe design is for minor events. It may have a minor event hydraulic grade line that might look like this. So that's what the existing system is doing. And then we go and we develop and we connect in our proposed stormwater system. So this is probably what's going to happen. We're adding a bit more water, but that water doesn't really reach the surface. It performs underground as it should, so everything's okay. But what happens if our existing system actually had a bit more stormwater running through there and those water levels were actually higher than what they were previously? If we go and construct our pit pipe design and connect into this system, we can see that those levels are going to rise because that downstream water column is actually higher. So it's going to cause a bit of an upstream effect for our design, and our water levels are going to increase. But what if your existing system is already close to or at capacity? Now, especially in built-up areas, in larger CBD cities, this happens quite often. And if it's not thought about, it can be really detrimental on our design. And worse, if it goes unchecked and we build it, it can be detrimental for our community and our people as well, because it will cause flooding issues. So if your existing system is close to or at capacity, and then we try to connect our new system with more stormwater running through, what do you think is going to happen? Of course, we're going to force water where it can't go, so it will cause surcharge in our system and downstream as well. And this happens quite often as well. I've seen this in a lot of stormwater reviews where that downstream system wasn't properly considered or analysed, and that's what was actually happening. And yet, if you don't design for that, you might have a design that works, but in reality, this is what's going to happen, and you'll have surcharge and flooding issues. So in Australia, as a national approach, what we do is we recommend that the starting hydraulic grade line or your tailwater level should be 150 millimeters below the surface level. Now, the problem with this approach is that it is very conservative to start, but your existing system, it might be at capacity, and so that would be true, or your existing system might have more capacity, and so you might be over-engineering a solution. So the answer to this is, my opinion, I recommend that you talk with the authority, the municipality, the council that owns the stormwater system, because they are the best position to understand and give you advice on how that existing system is actually functioning. When you go through that conversation, then maybe you can do some analysis to work out what that level might be, or council might actually advise to you and say, we know that's a problem area and flooding occurs, so maybe a connection into that system is not a feasible option, or maybe you need to upgrade that existing system downstream. So when we look at the open channel model, and this will be just the last couple slides, and I think we'll finish for the night. So the open channel model, it assumes that your pipes are running as a series of connected open channels, which assumes that the water is not under pressure where you have that pressure head in your pits. The way that we do this is we use Manning's equation and the volumetric flow rate equation, or Q equals VA. And the good thing about this is you can use a nomograph or a design chart to actually estimate what those flows actually are. So here, you won't be able to read it quite on the screen, but each of those diagonal lines represents a pipe diameter. And then we have a pipe grade on the x-axis and our pipe discharge on the y-axis. So then you can just read off of this chart for any pipe design and then estimate based on a certain flow rate that you might have, like your inflow for your inlet pit. You can then estimate what size pipe you need at what grade to convey those flows. Now, this is for the open channel model, which is not suitable for detailed design. And I must stress that it's great for concepts or preliminary design, but you would need to do a more thorough, more complex analysis for detailed design and ultimately to build the pipes. But for a first pass to get an idea of what you might be looking at, this is a great method. And again, this design spreadsheet is included in our pipe design online course. This spreadsheet's and the chart that you see is completely dynamic as well. So as you enter in your different values, you'll get different readings on that chart. So it will just instantly give you those answers. So that nomograph, I'll give you another example here, and I'll show you just how to read this nomograph. And then I think that will probably wrap up for the night, and then I'll pass you back to James. So if you have one of these design charts, and we have a problem, let's say we need to pipe 100 litres a second, but we're limited to a maximum 1 in 50 or 2% grade. We come to the chart and we look at our 100 litres per second. That's what we need to discharge. We read across and then we look at our pipe grade at 1 in 50 and we read up. Now where these 2 points intersect, that will be, in this case, it's positioned between 225 and 300 millimeter diameter pipes. So in this case, a 225 diameter is slightly less. It's too small to convey the 100 litres a second. And a 300 mil diameter pipe will be able to convey slightly more than 100 litres a second. So we adopt the 300 millimeter pipe for that initial pipe reach. So you can see using these design charts, it becomes very quick and easy. Once you understand your inlet inflow, you can then work out what that pipe needs to be to convey that inflow through your system. So that's where we read across and we see in between those two pipes, and you take the greater of those two to make sure it has conveyance. We can also check the velocity on some of these design charts as well. The other diagonal lines that we see on this chart is between 1.5 and 2 meters a second. So it gives you an estimate of what that velocity might be as well. We can reverse engineer this as well. So rather than have a discharge that we need, we can use this chart in a different way to check the capacity of any given pipe diameter at any given grade. So as an example, if we want to know the maximum flow rate that we can get through a 450 millimeter diameter pipe at a 1% grade, we can read the 450 profile. We can look at our grade at 1%, and then where they intersect, you can read across and find out what that discharge rate is for that particular pipe at that grade. So in this case, a 450 diameter pipe at 1% grade will discharge 285 litres per second. So that's how we can use those design charts to do a very quick analysis for pipe design. All right, hopefully we've still got most people online and we've kept them for a while. I'll hand you over to James, but just before I do, I'd just like to say thanks for, again, having me tonight. And hopefully you've learned a little bit about stormwater, pit and pipe design. And I'm sure there's a lot of similarities. It doesn't have to be an Australian-based approach that we have here. This is something that we, problems and issues that we face all around the world. And a lot of these concepts and designs, I believe, are the same across many countries around the world as well. So I'll pass you over to James. Thank you very much.
Oh, amazing, amazing. Thank you very much, engineer, for taking us through this session. The 2 hours has been, you've educated us, you've entertained us, and what I like is the flow. Like we've started from getting the runoff, then we are tapping this water, and then after tapping it, we are directing it, and then after directing it, then again, we are knowing how will it channel it now to the right location. And one of my biggest takeaway was on connecting existing or connecting new stormwater pipes to existing this sewer systems. I think that is one of the, that is where we are in most countries, because we already have the existing systems that are already functioning. So it is very important for us to understand how do we connect them as we do the design. So thank you very much. I'm looking at the chat box, and I think, engineer, please, you can respond to this, just a minute. Timothy is asking, for the online courses, will certificates be offered upon completion? That is the first question, and specifically for inlet and pipe design.
Yes, every course that we have, once you complete the course, you can just request a certificate, and we provide a certificate. Here in Australia, we use CPD points, and basically 1 point for 1 hour of professional development. And so each certificate will have the number of hours for that particular course as well, which is great, because then we provide that to here, Engineers Australia, and that gives you a record of that professional development they undertook.
Super, super fantastic. I think that was well answered. The other question is, I'm not seeing anything else. The other one is, people are asking for you to be kind enough and share with them the slides. That is the question. That is the next question that I'm seeing. So
no problem at all. I'll send them through to you, James, over the next day or so, and then feel free to share with participants. Yeah, absolutely.
Absolutely. Thank you. Thank you very much. For the interest of time, we are very honored for you creating this time. I know it's already night at your place, so thank you very much for your time.
Yeah, of course.
Yeah. So we really appreciate these. And you guys, now you know I'm not the software guy. You were expecting me. I'm not, this was not about the softwares guy. It was now engineer taking us through the entire process. And then the product that you get from this, now the result from this design, that is when now you can be able to take over to model it in your various softwares. So thank you very much. The recording shall also be provided on YouTube, and it will be accessible, by the way, by tomorrow, so that also you can go through this. So thank you very much. I would like to see one of my beautiful people here, Captain Baron, to give a vote of thanks. Then we can conclude the session. Baron, please take it away.
Guys, we really like to appreciate the engineer Sean Quilty. Thank you so much for your time. This was immensely beneficial to us, and we really appreciate you. Thank you so much, and we will be in touch. We'll be in touch. And also, on behalf of the Roads Up team, we really thank you for carving up this time to educate us. We know you're a very busy man, so we really appreciate you. And I know all of my people here, the chat box, they're already clapping and thanking. So thank you so much. And we also would like to thank sorry for that. And we also like to thank the Roads Up, Engineer James, for making this possible. I mean, we didn't even know about this, but thank you so much, Engineer, for allowing us this opportunity to learn. So we really appreciate you. So thank you so much. Thank you so much, Engineer.
All right, thank you. Okay, thank you. Sean, parting shot for my beautiful people. What do you have to say? A parting shot?
Oh yes, no, look, just again, thanks so much for having me. I love what we're doing here, where first we're connecting the theory with the practice, right? We're connecting the theoretical knowledge into the software, and we can understand how we can use those practices when we start modeling as well, which is great. But the thing that I love about this is that we can do this from Australia right through to Africa, and we looked at all the countries there. And I think this is the future of engineering. No longer is it just within your jurisdiction, even your particular country. I think we're all, we're all experiencing all the different sort of climate change scenarios that we're looking at. Flooding, like you mentioned before, we're getting more and more flooding issues, more frequent, more severe. And I think we need to come together at a global scale and really learn from each other, lift each other up, and just take away knowledge from everyone. And I know for a fact, the more that we chat with everyone over there, I'm going to learn a lot more, and I'll become a better engineer. And I hope that we'll have better communities and vice versa. So no, thank you very much for this opportunity. It's been great.
Absolutely. Thank you very much. And the meeting is adjourned. And we wish you a good night, sir. So you can now go and rest. We are very happy.
Yes, will
Go
do.
and rest. We
Thank
release
you.
you.
Thanks, James.
Thank you.
Appreciate
Thank
it.
you. Thank you. Thank you. Thank you very much.